All right, we are moving on with lesson 5.6. This is the last lesson of chapter 5. We are tying everything that we learned throughout this chapter and going to be able to do proof charts based off of triangle congruence. Okay, just a quick review. Do now from last lesson. Are these triangles congruent? If so, by which theorem? SSS, SAS, ASA, AAS, or HL? So let's take a look. All right, our first example over here. All right, again, always make sure that we match up. We have 1 and 1. Those are congruent sides. We have angle, angle. Label it with A or S for A for angle, S for side. And we see that 2 matches 2, so those are congruent sides. But remember, they also have to match up. So we go in order. We see that we have S, A, S. Always go in order by never lifting up your pencil. And we start at the same thing, S, A, S. We see that they do match, so this is a yes. And we know that they're congruent based off of the SAS congruency theorem. Over here, we see that 1 matches 1. Those are sides. 2 matches 2. Those are also sides. The picture itself doesn't give us anything else based off of sides or angles. But remember, segment AC, all right, segment AC here in the middle, that is a part of this triangle and a part of this triangle, which means if it's the exact same line in 2 different triangles, that means that it is in fact a congruent side because it's the same exact line. So this one is congruent due to SSS or side, side, side. Okay, just a quick review of what we learned last lesson. Also here, if you go into Canvas, all right, updated with chapter 5, you can pull up the notes for 5.6. That's what we're talking about here today. So just real quick, going over some review vocab words that we've learned earlier on in the school year, but they're going to pop back up during this lesson. Vertical angles, remember, angles that are on opposite sides of intersecting lines, and we know that vertical angles are always congruent. Reflexive property, x is equal to x. The way that it's used with triangles means that the same line is congruent to itself, similar to what we just saw in that warm-up, in that do now. If the same exact line is used in multiple different triangles, it's obviously going to be congruent to itself. Definition of a bisector divides either a line or an angle into 2 equal and congruent parts. Right, and also to review corresponding angles. Angles are always in the same relative position, always congruent, right? This angle is above and to the right of the line. This angle is above and to the right of the line. Alternate interior angles, angles that are inside parallel lines and on opposite sides of the transversal. And remember, those are also always congruent. So sometimes you can see triangles being involved that are a part of parallel lines as well. So it's important to refresh on these types of angles as well. Okay, there's nothing really necessarily new in this lesson. It's just a bunch of examples of working with proofs with triangles and how we can put them all together. Okay, similar to what we had when we did proofs before, you'll always be given a word bank to choose your correct answers from. All right, so let's just get going with these examples. Remember, given always goes first. All right, given, and let's take a look at what's given to us, right? AE bisects BD. So AE, right, this segment AE bisects, which means cuts in half BD. So if it cuts in half, we know that now BC is going to be congruent to CD, all right? BC is congruent to CD, which we see as the exact next step, and that's because of the definition of a bisector. So we would write definition of bisector. And just like always, I apologize for that poor handwriting. Okay. BD bisects AE. Look at that, ladies and gentlemen. That was a second piece of given information. So we use given again. All right. And now it's basically just saying the opposite of what we already just did. Right, let's say if we use a different color here, it's saying that BD, so this entire segment here, bisects or cuts in half segment AE, which now means that segment AC has to be congruent to segment CE because C is that midpoint, and that's what we have here. So once again, that there is definition of a bisector. Okay, and now let's take a look. It says that angle ACB is congruent to angle ECD. If we use a third color now, right, that's ACB. That is this angle right here is congruent to ECD. Oh my goodness, I'm so sorry. I totally misread that in my head, right? ACB, that's this angle here, is congruent to ECD, which is this angle right here, right? And that was not given to us, but we know that that is true. These are two congruent angles. Why? Because they are vertical angles, right? Vertical angles. And now we have enough information to prove that these two triangles are congruent by using one of our 5 congruence theorems that we learned about in last lesson. So if you see, we have side, or here, let me do that in a different color. Why not? Okay, it's not letting me. Oh, there we go. All right, this is now side, angle, side, and we see that we have side, angle, side. So we can conclude that these are congruent based off of the side, angle, side theorem. Okay, first example, good. Second example, okay, let's take a look. Given segment AD is congruent to segment BC. All right, let's draw that. I always like to draw first. Segment AD, where do we see that? Segment AD, that is that entire line is congruent to segment BC, which is that entire line. So I'm going to draw it in the same color, right? We know that that is there. Okay. Also notice that is not written in our first statement. So we know that that is going to be what we should write first. Segment AD is congruent to segment BC. And our reason for that is that because that is given. All right, and given to us next is AC is congruent to AC. Well, if you think about it, AC and AC are literally the same, right? And we know that that is obviously true because it's the same line. But notice AC is a part of triangle ACD, and it's also a part of triangle of ABC, right? So it's the same line, once again, used for 2 separate triangles, right? So that there is what we call the reflexive property, right? They are equal, it's congruent and equal to itself. That is the reflexive property. Okay, next it says angles ACD and CAB are both right angles. So again, let's use a different color. It says that that is a right angle and that is a right angle. We see that that is actually given to us, so we can just write the word given here. All right, now we have a right angle and we know 2 side lengths are equal to each other. Well, remember, whenever you have a right angle, always check and see if it's going to be hypotenuse leg. Excuse me, remember the hypotenuse is always opposite from the right angle. And if we draw arrows opposite from our right angles, we see indeed that the hypotenuse of both of those triangles are congruent to each other. And then we see that AC is the leg for both separate triangles, so that's congruent to each other. So therefore, we can conclude that these 2 triangles are congruent based off of the HL theorem. Okay, next one, given MA is congruent to segment HV. So again, let's draw that out. MA, where's MA? MA is this diagonal line here. Right, that is congruent to HV, which is this diagonal line here. All right, I'll draw them in the same color so that way we know that that is given. The next reason is given, which means that we know we're going to write what goes next here. That segment, oh, I'm sorry, I mixed them up. But so that what we just drew, MA is congruent to HA is going second here. Okay, now the second piece of given information up here, which was weirdly put first, all right, so it doesn't really matter the order, but let's just go through it now. All right, so now MV is congruent to HA. We see that MV is here, HA is here, so now we know that those 2 lines are congruent to each other. Okay, and now it says that VA is congruent to AV. So again, if we use a third color, right? VA is congruent to AV. Ladies and gentlemen, those are literally the exact same lines. All they did was just rearrange the order, VA and AV. And we know that the same line, if it's used in two different triangles, they are congruent based off of the reflexive property. Right, and now if you take a look, we have side, side, side. 1 matches 1, 2 matches 2, and 3 is literally the same exact line. So we can prove that these are congruent based off of the side, 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 or SSS theorem. Okay, next one. Segment AE bisects BD. Remember, bisects means cut in half. So AE, where's AE? A is this diagonal line here, bisects BD. So that means that BC and CD are congruent to each other. Okay, so notice this one's completely empty. So let's write that first. AE bisects BD. We know that that is always our given reason. And based off of that, we now can conclude that segment BC is congruent to segment CD. And we know that's true because of the definition of a bisector. Okay, now we need to look at our second piece of given information. It says that segment AB and segment DE are parallel. Remember, this symbol means parallel. So if you want, you can draw little arrows on that, right? Those now are parallel, okay? And from here, remember, we just talked about parallel lines. Remember, if it makes it easier, draw this as if these were continuing on. Right, now we have two parallel lines and a transversal, ladies and gentlemen, right? We have a transversal. So based off of this, we need to write this saying that AB is parallel to segment DE. I believe I'm now using too many lines, right? But we know that that's given. Okay, so I realize now that this should also be included up here, but it's okay. No big deal. We'll just use an extra line. Okay, and because of this, now we can conclude and confirm that angle CAB must be congruent to angle CED. Right? These two angles, we know for sure that those are congruent because they are alternate interior angles. Okay, and now just by looking at the picture, right, we can also conclude, if again we use that third color, right, that this angle is going to be congruent to this angle here. Why? Because they are vertical angles. So now we would say angle ACB is congruent to angle DCE. And we know that that's true because those are vertical angles, and we know that they are always congruent to each other. So now, again, like I said, I used too many lines. We have to write one more. Remember, when we write our congruency statements based off of triangles, we have to make sure that they are matching. So if we say triangle ABC, we have to say that it is congruent to triangle EDC. And how can we tell? Let's take a look. We see that we have angle side matching with angle side. So based off of the AAS theorem. Okay, and that's all I have, right? Just a bunch of examples. This is a little bit difficult, I understand, but make sure you bring lots of questions with you to class. Go Mustangs.